Okay, we're wanting to construct graphs of these two functions. Starting with the first one, we can construct the graph of the exponential function in the usual manner. Our x-axis here, a y-axis here. We put all the construction lines in it. Now the ones that matter, this one at this point are well, 4 x equals 2, x equals negative 2. I would expect to see that. When I say construct a graph, we've learned how to construct a graph of the exponential function in a 4x4 box. Okay. And that's our basic structure. And of course, we've seen that the points that you got here agree perfectly with the points you get if you plug in x equals negative 2, negative 1, 0, 1, 2. So the points that we get from the construction agree with the points in the table. So this is y equals 2 to the x. We could do a couple more construction lines. Y equals 2. Y equals 1. So we go down to 1/2 and 1/4. Yep. But I'm not going to draw them in. If you actually have these three and have them accurately placed, it's going to work for the other two. Okay. So just for a quick graph to visualize, to use as a basis for the real transformation, we can do this. Okay. And I'll include the red dot. I'll do that in the support course because I know it's everybody can. People in other classes have this to do. Okay. Anyhow, so what happens if we do y equals negative 2 to the x? Well, the line y equals 4 becomes a line y equals negative 4, right? So y is going to be the negative 2 to the x. So now nothing changes the x equals 2 line, the x equals negative 2 line. But of course, when x equals negative 2, this point up here in the upper corner flips down to the lower corner. And of course, that's because negative 2 to the x will give you y values that are just negatives of the y values you get here. So have y equals negative 2 to the x. And then we could do our construction lines that go like this. Okay, as we get twice as close to the red dot. The red dot is going to stay here. The red dot is the origin. And if you flip the coordinates of the origin over, you still get the origin, right? Flip 0, you still get 0. So right there would be a pretty good approximation of a graph of y equals negative 2 to the x. Now what's negative 2 to the x minus 3? Well, minus 3 takes every point 3 units lower. So it takes the red dot at the origin down here to the line, y equals negative 3. So basically, this graph shifts 3 units lower. So if you get your x equals negative 2, and x equals 2 lines, still 4x4 rectangle, so y would have to become -7 in order to maintain the shape of the rectangle. And of course, y equals -4. If you lower it 3 units, becomes y equals -7. So here's our graph. And again, we can do a couple of construction lines if we want to make it a little more accurate. My first halfway was a little bit. Yeah, maybe maybe a little bit aggressive. Okay. So right there is a graph of y equals -2 to the x -3. Do we say we flip? And then we shift down 3. The asymptote is y equals -3. If you're going to do a good graph, you note that that's their asymptote, which reinforces the fact that it's an asymptote, which makes it more likely you'll understand asymptotes when you see them later. And I would recommend you do something to show the scale. And labeling these horizontal and vertical lines, I've shown the scale. Now, you know, when you first learn to do graphs, you scale count over 10 units here, and you probably don't even do it by hand. Someone gives you a picture, piece of paper with a grid on it, so you don't have to do anything. That's not a bad first step. You should get away from the grid to where you can sketch it by hand. And I'm not sure that's being done. I mean, the whole secondary education. It's especially important for people who are going to go into STEM fields. You got to be able to do back of the envelope stuff. And hopefully to do it well enough that you can start visualizing it. And different people have different visualization skills. Plenty of people who have terrible visualization skills and good envelope skills. So, and vice versa. You're not in the STEM area, that's okay. You still finance for bacteria growth, for all kinds of things that you saw in the first section that are modeled by exponential functions. It's important to understand exponential functions. I'll say it might be important. Okay. Can't guarantee it'll be important, but I certainly think that if you're in any kind of field with any rigor, it's going to be important at some point. Be useful. Okay. Now, this next one, there's a little bit of a curveball here, something we haven't even talked about because we haven't talked about it. We didn't talk about it at the beginning of the semester because it doesn't occur until over halfway through the semester, but it just occurred. Okay. So we've got it now, and we got to deal with it. Is this 1/2 in front of x? We haven't seen anything like that. Okay, let's put this in kind of format. This is okay. -1 says you're going to keep your scale, but you're going to flip. H equals 0 means you're not shifting it right or left. And usually we don't bother doing much shifting of exponential functions, but sometimes we do. I talked about that a little bit last time. Okay, k equals -3 means we shift down 3 units because we're subtracting, we're adding a -3 to whatever the y value of the rest of this would have been. Okay. So the rest of this is here. Plus k is -3, that's we're shifted down. Now we have y equals 2 to the 1/2 x is 2. You can't write this as an a f of x minus h plus k function. F of x equal to your toolkit 2 to the x function. Okay. You have to write this as y equals a f of c times x minus h plus k, which is a little tricky in some ways. Okay. Well, we still have, in this case, we have a equal 1. This is the 2 raised to the power function. This has coefficient 1. And k equals -3. We haven't added or subtracted anything to x, so h equals 0. So what's the value of c? Write it down. C equals, if you know. Yes. Okay, so we've gone a little bit. I forgot to start the recorder. But here we've identified A, K, H, and C. C is 1/2 because, well, look at it. For the f of x equals 2 to the x function, this becomes A times 2 raised to the c times x minus h plus k. H is 0, so this is just x. So you just have c times x. Well, it's 1/2 x. Take 1/2 x minus 0. You get 2 to the 1/2 x plus 2 with these numbers. And that's pretty straightforward. So the effect of that 1/2 x is to horizontally compress or expand the graph. Okay, if the number is less than 1, it expands it. It's greater than 1, it compresses it. So call that, I call it C, I call it a horizontal compression factor, really compression / expansion factor. Because it can do either depending. And as far as that goes, it can also flip the graph because we put a -1/2 in there, right? About the x-axis. So you start with your basic exponential function. I expanded it a little bit too much, but you go from x equals 2 up to x equals 4, from x equals -2 to x equals -4. Why? Because the compression of 1/2 is an expansion of 1 over 1/2, which is 2. Okay. If your compression was 2, you would squeeze the thing in. Instead of going from -2 to 2, you go from -1 to 1. You're expanding, so instead of going from -2 to 2, you go from -4 to 4. So it makes the graph, spreads the graph out this way. You then are going to need to shift it up 2 units. Okay, so you're going to need the line y equals 2. Because if you shift the asymptote, which is the x-axis, up 2 units, that's what you get. And then you draw the same rectangle. And I did not scale the rectangle here. Well, my expansion by 2 is more like an expansion by 3 or 3.5. And this will be your line. This will be your line y equals 6. Now you have this rectangle, let me kind of whatever. Now you construct graph here and there. This graph would be y equals 2 to the 1/2 x. This graph is y equals 2 to the 1/2 x plus 2. Does that halfway make sense? Oh, there. Okay, well, there's more to constructing graphs, but you also want to identify the asymptote. This one's so messed up, I'm going to try to insert the asymptote, okay? But we would label the y equals 2 line as the asymptote. Sort of approaches. Okay. We'll move on then. Have you log? First of all, let's start with the graph or with the table for y equals 3 to the n. So fill this table in for me real quickly. And then fill in the table of the inverse function. The inverse of y equals 3 to the x. First, take this table, then do what you need to do the inverse. And then maybe even sketch a graph of the function and its inverse. First of all, what do we mean by an inverse function? A lot of people will get used to doing an inverse of something with a formula, okay? Where you switch x and y and then solve for y, okay? And that's all they remember. The thing you want to remember is that inverses switch x and y. And that's why you switch x and y and then solve for y, okay? But the definition is inverses switch x and y. Now, I could do more mathematically rigorous definition, but that's good enough for what we need right now. Okay. So when I tell you to do the inverse table, and I think everybody did it, but when you do the inverse table, first of all, get your arithmetic right, because I saw a couple of mistakes with negative exponents. You can't do that, okay? Got to understand those negative exponents. You're not going to understand the exponential. Anyhow, we get the table and we switch the x and y columns. And now we can make a graph of both of these functions. So, first place, I'm going to need a 9x2 rectangle to accommodate these points. So we use 4x4 rectangle for almost all the basic functions we've really constructed. And I'm going to do a 9x4. So I'm going to try to make it more or less scale. That's 4, that's 4, 2. Then I'm going to put it down the middle. Right here. Right here. This is y-axis and this is the x-axis because the red dot is still in the middle. Up here. It's just like what we would do for 2 to the x, except we got a longer rectangle. And then we can subdivide here. Well, we don't really want to subdivide in half because our y values, we start at the top, go 3 times closer to 0. Okay, so we're at y equals 9. Go 3 times closer. That means this is about a third of 9. It's a little high. And then we do a third of that. and a third of that. A third of that, and we end up with a point way down here. Then we end up with a point of 1. Let's see. This would be our y equals 3 line. This would be our y equals 1 line here. That's where the the y-intercept is going to be. And then we're going to have one out here of x equals 2. And then we're going to have a couple of points in between. We just got these 3 points as before. We can pretty well see what this graph is going to look like. Okay. Got to be the smoothest possible curve, goes through these 3 points. Well, that's fine. Now, what are we going to do for the inverse? We're going to need a rectangle that goes 9 units in the x direction. Okay? That means and from -2 to 2 on y. So we're going to put y equals -2 about here. Y equals 2 will go down here. X goes from a little more than 0 up to 9, so we've got to have a line for x equals 9. That's going to be out about here. Maybe a little further, it's not too bad. Okay. And that's going to put us this rectangle. It's the same size and shape as this rectangle. It's flipped over on its side, but it's kind of flipped and then flipped, rotated out of the board. Okay. And then, we can do our construction, but we can just take each of these points and switch the x and y coordinates. This point is on the line x equals 2 and y equals the line y equals 9. Corresponding point is going to be on the line y equals 2 and x equals 9, and that's going to put it here. That makes sense? Because x and y are being switched. So y equals 9 become x equals 9. We've got to be on this line. X equals 2 becomes y equals 2, puts us on this line. There's our. Then the y-intercept is x equals 0, y equals 1, right? Okay. So here's line x equals 0. And here's the line y equals 1. That's going to go to the line x equals 0 will become the line y equals 0. Which is the x-axis. So now let's label this as the line y equals 0. Okay, so again, this line is on x equals 0 line, which is the y-axis. That's going to become the y equals 0 line when we switch x and y. And the y equals 1 line will become the x equals 1 line. We haven't got what it's here. We have to label it wrong. So here's the x equals 1 line. That puts us here. Okay. This point is at x equals 0. Sorry, y equals x equals -2. I'm sorry, and y equals 1/9. Okay, -2, 1/9. You gotta have 1/9 -2. So 1/9 is too close to the y-axis. -2 is here. We get these points, and now there's our graph. That makes sense? Okay. And what do we call the inverse of x equals y to the third? Call that y equals log base 3 of x. Okay. If we draw the line y equals x, so excuse me, right? If this is done to scale, now my 9 units there was bigger than my 9 units here. Things are a little distorted. I got a little carried away. But a line segment connecting this point and this point will ideally be cut in half by the y equals x line. In other words, this point should be just as far on this side of the y equals x line as this point is on the other side. Didn't turn out that way because I wasn't careful. Looks a little better between these two points, right? And looks doesn't look too bad between these two points, but my 9 got carried away. You're going to see that in your text. That's an important characteristic. It's an important image. It's important to understand that and always know that that's how inverse functions compare with the original functions. If you have equal scales, if the scale is distorted, or I kind of distorted that a little bit, then this is a little too far from the line of comparables. Okay. Now I could do y equals 2 to the x and log base 2. Okay, I just make the table for 2 to the x, flip them, that would be the log base 2 table, and we could do the graph. Okay, well, okay, well, the y equals 2 to the x graph, we just go up like here. And we compare these previously. It would look something like this. And down here, we could do the graph of y equals log base 2 of x, which would go something like this. Come out to x equals this point. Because this point would correspond to this point. And the graph looks like this. That makes sense? Okay. I think I mentioned last time that e to the x lies between 2 to the x and 3 to the x. So the graph of e to the x that and this, how I can get them right. Y equals e to the x is going to have a graph. Might look like this. Well, I take this point, put it down here, do all the rest of it. I'm going to find the graph of the log base d function lies between these two. Now, this point should actually be a little further out that way. But just thematically, okay. Y equals log base e of x, also called ln of x, natural log of x. E is the most natural number in the world. And the natural log of b is the log basically, the natural log function is also extremely natural. As you won't really appreciate until you've taken a good calculus course, if that's in the future. Okay. But if you do have one in the future, take care of the tension of everything you learn. Okay. Well, there we have three logarithmic functions. Log base 2, and then log base 3, extended out quite a bit further, and then log base e or natural log in between the two. We've already done problems involving base e without any real explanation of what e means. Okay, there's some explanation. I'd like to give you an explanation of what e means, and I will. We can work it in standard and pre-calculus, but do the various factors. You can't do everything without the standard. One of my favorite things I love to do. It's not that hard, it just takes a little time. Okay. Now, what are logarithms good for? You understand the basic thing about logarithms, easy switch x and y. Okay. From that, you can get this statement. Okay. Here, the log function is acting on A. Okay. And it gives you the result C. Here, the exponential function is acting on C and it gives you the result A. Okay. What this one acts on is what this one gives you. What this one gives you is what this one acts on. That means the log function acts on x and gives you y. then the exponential function acts on y gives you x. See how that's switching x and y? What's being acted on here is what you're given, is what you get from the function here. And what you get from the function here is what you're acting on here. Log function. Well, you know you had to use your calculator to evaluate the exponential function, didn't you? Did do the assignment we had to do exponential functions, E, right? Did, am I mixed up? Hold on. Okay. Now, this switches x and y. This. So for example, let's write here's an equation. These are equations actually. Okay. A equals what, B equals what, C equals what in this form. Write that out. Okay, everybody got it. A is 3x plus 4, B is 4, C is 7. How do you identify it? B is subscript of the log, that's 4. The A is what the log is acting on. In this case, that's 3x plus 5. And the C is what's on the other side of the equal sign, that's 7. So there you have it. Now, let's ask everybody to write this one out. These are those values of A, B, and C. Okay, well, I would pick C for 7. You get B to the C, which would be 4 to the 7, equals A, which is 3x plus 5. Everybody knows that 4 to the 7 is 16,384. If I did that correctly on my head, 50-50 chance, but it's close if it's not right. Okay. Then you can easily solve that for x, right? This is not easy to solve for x. They know way you can solve this. Okay, until you put it in this form. Okay, similarly, let's try three to the 5x minus 2 equals 12. You're going to identify A, B, and C, and then you're going to write in log form. Okay. This is the crux of everything we're going to do with logarithmic and exponential equations. It's unimaginably important, and it's really easy. So I just gave the advice, when you do the homework, don't have this written on a piece of paper somewhere and fail to write it out every time you do the problem, okay? Write it out. First 3 times, you're going to have to look at the paper, okay? By about the 3rd time, depending how quickly you pick it up, different people have different visual memories and stuff like that. It's going to take some people longer than others. But about the 3rd time, maybe you start trying to write it out yourself, then you compare. You say, no, I screwed up, it's got to be this. Now I'm seeing the pattern. Next time you write it out, you're more likely to get it right. And by the time you've done 5 or 6 problems, pretty much know how to write this out, so you won't get onto the test, because I'm not going to tell you this on the test. Okay? It's an inverse function relationship. It's related to everything. Pull it all together and understand it. It's very important. Okay? But it's easy. Okay? So keep pulling it out of that way. Right? That's how you remember it. Okay, so there's our equation, and that's a very easy equation to solve. You subtract 5 from both sides. Then you divide both sides by 3 and you get this. Okay? Now another thing. I want to bring this back to the log and natural log. Okay? Because those are the things that your calculator has. Now your calculator probably allows you to do a log base 12. Okay? So use this. Start out right here. That says log A over log B. That's what log base B of A is. It's log A divided by log B. And you calculate any calculator, except the kind you give the 4-year-olds, should has a log key and a natural log key. LN, a natural log. Okay. Calculate log to any base. Calculate the log of a number, any base. Do the log of the number divided by the log of the base, which is the same thing as the natural log of the number divided by the natural log of the base. Okay. Side comment. Each of these graphs here is just a vertical stretch of okay, vertical stretch or compression. And each of these graphs is just a horizontal stretch or compression, each of the others. Okay. And that's why the log of A over log of B is equal to the natural log of A over natural log of B, because the log of A has some constant stretch compared to the natural log. It's the same in the numerator as in the denominator, so it doesn't matter. And if you understand that, that's a pretty good thing to understand. Okay. I mean, it's not that hard. It's a bit of knowledge that most people don't really relate to. Anyhow, you can do this. Now, what's the log base 3 of 12? Well, it really comes down to the question of what power of 3 gives you 12? Well, 12 is between 2 powers of 3, right? What 2 powers of 3 is 12 lie between? Can you show me? Fingers in one hand, fingers in another. Yeah, be between the second and third power. Second power of 3 is 9. The third power is 27. Okay. Tells you log base 3 of 12 is probably closer to 2 than it is to 3. Okay. So let's just say that's approximately equal to maybe 2.1 minus 5 over 3. And I didn't make any effort to make that 2.1 accurate. Okay. But the way the log behaves, it's concave this way. Now, does that mean the 2.1 is low or that it's high? It's worth thinking about. I'm not going to talk about it. You subtract that, and you get 2.9 over 3, which is then going to be 0.96 repeated. But what this stands approximately 0.97. And that would be the solution. Now, since that's a solution, we put 0.97 in here for x. 5 times that is 4.7. 4.7 minus 2 is 2.7. Is 3 to the 2.7 equal to 12? Doesn't look like it. So maybe I did something wrong. But the point I'm making is check. Okay. Oh, wait a minute, 2.9. Well, that'd be even worse. So something's wrong with some of these numbers, but you can put them in your calculator and whatever number you get out here, put in here and see if you get 12. Okay. And if you don't, and you're sure every calculation is right, then check out how you solve this. Last thing, keep writing log base 3 of 12. Don't punch that into the calculator and write out a big long number here. Keep it as log base 312 until you find an expression for x. Then start putting things in your calculator. Okay? It's neater, it's less aggravating, and it's less vulnerable to writing down the numbers wrong. Okay? Less prone to error. That says, hang on.